Okay, off we go. So, last time we were talking about how to address questions like this. We got a domain for an integral which is of a shape that causes the subsequent bounds that you would write down. I guess that should still be in green. These bounds that you write down to be pretty undesirable. Right? And not that it can't be done, but it's inconvenient. So the big idea was to realize that we can fairly easily view that as being an image by way of the polar coordinates conversion formulas, aka the polar coordinates change of variables function. Right? And it's the image of a rectangle, which means we get constant bounds, and which makes this calculation work easily. So a big idea. We streamlined that by making the observations that all the slicing process that you do in the r theta plane, that whole slicing process, you can just explicitly see it already in the xy plane. And so you don't have to draw the pullback. You can just say, all right, well, I'm going to change this. Let's see how to say it. I'm not going to slice this up in rectangular coordinates. You just say, I'm going to slice it up in polar coordinates. I recognize that there is actually a change of variables involved. Therefore, there is a stretching factor. You got to put that in there. It's really important. That's the thing that makes this work, right? This is the multivariable calculus idea of doing an integral in polar coordinates. So extremely, extremely important. By the way, just to emphasize on an exam, just putting down the correct stretching factor in there worth several points, probably. Right? So it's a big deal. Make sure not to forget it. It's so easy to accidentally forget that, and then you'll be mad at yourself. If you say we're going to do this in polar coordinates, and I'll just do my slicing in polar coordinates, I can explicitly see my theta bounds right there in the picture, just from understanding what these theta slices look like, and likewise for the r slices. Okay, so that's where we left off. What we have today then is a bunch of examples, basically. Examples and sort of related tips and tricks. So anyway, here we go. Let's see the next example. Here our domain is going to be this disk, the unit disk. And let's think about, okay, how would I slice this up in polar coordinates? And there's different ways to think about it. A pretty natural, easy way to think about it is to think of theta as starting at 0, and then theta, your subsequent slices, you can see we just kind of keep going and going, right? And then et cetera, and it makes its way all the way around, and you stop when you're done, right? You're done when you've finished sort of sweeping out the entire domain that you're interested in, and of course that happens at 2 pi. So the integral starts at 0 and ends at 2 pi in your theta slices. By the way, it's a good sort of example to always keep in mind. If you have a domain that I'm going to say surrounds the origin. So there's the origin. Notice that our domain kind of surrounds it entirely. Right? The origin's not sort of on the edge. The origin's not external to our domain, right? If the entire origin is surrounded, then in some sense you're always going to kind of have to go all the way around. And thus you'll always have 0 to 2 pi in such a case. So nice little sort of convenience to keep on the lookout for. I emphasize, don't forget the R stretching factor. Hugely important. So easy to remember. So easy to forget. Right? So make sure to put a special focus on making sure you remember it. I'll come back to that again in just a moment. By the way, let's also talk through the R bounds. So we've already agreed that theta goes 0 to 2 pi. We'll, just for graphical convenience, draw here a representative value of theta. And now let's think about, where does R start and end? Well, we start at the origin, where of course R is 0. And we're going to end at that point, which is on the unit circle, right there in the picture. And being as it's on the unit circle, that's where r is 1, thus giving me my upper bound. Everybody happy? Everything else is single variable calculus. Okay, moving along. A couple of tips. Convenient tricks. Good news, even though you have a choice of 2 different orders, in almost all cases, you should do dr d theta. Dr on the inside, d theta on the outside. And the reason is, when there is a relationship between r and theta that makes polar coordinates useful in the first place, it is typically the case, it's easier to view r as a function of theta than to view theta as a function of r. Right? So, for example, if r is sine theta, would you rather deal with r equals sine theta or theta equals arc sine of r, and then you'd have to worry about the multiple values and is arc sine giving you the right value? Oh, it's a nightmare of inconvenience. Plus, arc sine is hard to integrate with. Right? So it's almost always, I don't want to say always, very rare, though, to have a counterexample. So I would encourage you to just reflexively use this ordering of the differentials. Okay, next observation. This is a hack. This is something I decided when I was probably about y'all's age, that I would just never write down the differentials, dr d theta, by themselves. After all, if you write this down, you're doing so because you're doing the integral in polar coordinates. And if you're doing the integral in polar coordinates, you have to have your stretching factor in there, right? That's part of what makes it work. That's the critical element that's the multivariable calculus point that allows for this to work. It is a change of variables. So my little hack, I strongly urge you to do the same, is to just don't ever write down dr d theta by themselves. You'll never need dr d theta by themselves, right? So rather always write down this whole thing, r dr d theta, all together, all at once. If you always write r dr d theta together all at once, you'll never forget the r. So anyway. All right, and you don't have to, right? But to the counterpoint of, oh, don't worry, I'll remember, I'll point out, I'm sure that's what every student who forgot it thought. I'm just saying, right? You do whatever you want to do, but this is a helpful hack. Okay, as previously discussed, that r is worth a lot of points. So real quick, let me just point out different points of view you could take on this. You can view this glass half empty, or you can view it as glass half full. The glass half empty point of view is, I get stung, I lose a lot of points just for forgetting one little thing. That is true, I suppose. The glass half full point of view on this is, hey, all I got to do is just write down the letter r next to dr d theta. Boom, that's points right there. Several, probably. Okay. So I encourage the glass half full point of view. Okay, here's another example. This is just kind of for dramatic purposes, but shows how useful polar coordinates can be. Let's suppose that our domain is this, we'll call an annulus. Which I compulsively feel the need to color in all the way. There we go. So how would we do this integral? Let me point out a couple options that don't work well, if at all. One option is to view this as being this larger disk minus the smaller disk. and I can compute the yellow integral, I would think, and I can compute the purple integral, I would think, and then if I'm interested in the annulus, could I just take yellow minus purple? Seems like it ought to work. Y'all have done things of this sort in single variable calculus classes. Seems clever and strategic. Crash and burn doesn't work at all, because if you look at the origin itself, at the origin, the integrand is undefined. And that's not how integrals work, right? The way we have integrals defined, and this is a nasty problem. In fact, the way we have integrals defined, we literally do not even have a definition of what such an integral, either of these integrals, would mean. So this is a dead end. It does not work. Okay, in this case. All right, so fine, losing. Okay, so here's the next idea. We can chop it up. And we don't hit any corners in a slicing process, but you do, as you slice, you get what I like to think of as a side swipe, right? So that slice kind of side swipes that piece of boundary, and the reality is that at that point, as a result, you have to kind of start new integrals. For the green integral and for the blue integral, that curve is where your upper bound comes from. But for the green integral, the lower bound is there. For the blue integral, the lower bound is there. They're different. You can't write them with the same iterated integral. So totally different domains. And then furthermore, that piece and that piece. So that's four separate, and I'll point out actually pretty hard integrals, because look at the curves that define the bounds. They're circles, which means you're going to be dealing with square roots, and nobody wants that. Okay, all right, so again, not good. But look how easy it is to do this in polar coordinates. There's nothing to it. Here's what a theta slice looks like. Arbitrary theta slice. I think it's a pretty easy pitch that theta goes all the way around from 0 to 2 pi. And then, for a given fixed value of theta, such as I have there, this point tells me my lower bound for r. That point is on this curve, which has that equation, in which I can solve for r very easily. And is that a...
Yeah,
okay, yeah. Mm-hmm.
I was going to ask, because you did the same notation above, that all equals notation with the backslash, that's just area between two lines?
Oh, down here?
Yeah.
Oh, yeah. Let's. I'll get to that when we get there. Yeah.
I know with the top as well. Yeah.
Yeah. We'll get to that. That's a separate example. Yeah. Okay. Yeah. So the lower bound from that point, the upper bound comes from that point, which is on this curve, which has that equation, in which I can solve for r to get that upper bound. And it's just easy as pie. Right? Nothing to it. And in fact, not only does that slicing work really easily, but the stretching factor that you'll notice I've got in here, you can't tell from the way it's written, but I did write those down all together. Right? That's how I protect myself when I can make myself remember. But that combines with how my integrand converted into polar coordinates to very conveniently cancel and turn this into the world's easiest integral. So this is awesome, super convenient, and way, way better than either one of these previous attempts that crashed and burned. Okay, next example. Let's talk about your question. So this right here just means take whatever you've got there, which is this, and then subtract off, eliminate any part of it which is in here, right? So that says anything that's in this red disk I'm going to remove, and when I take the green and remove all of the green points that are also red, the result is this kind of ellipse-shaped domain there. Is that cool? A partial eclipse. Yeah.
I had a quick question about the example above.
Okay.
How did you get the 1 over r?
Oh, yeah. So that's just rewriting the integrand of the original integral. So keep in mind, well, I guess I didn't quite get this on the page. Okay, let me do that. Okay, that helps. Yeah. Okay, so the integrand, you just have to rewrite in terms of polar coordinates. And yeah. Okay. And convenient existing formula. Yeah. Yeah. Okay, so this example here, there's our domain, and let's think about how to describe this. Now again, you can do this in rectangular coordinates. Again, you're going to have multiple pieces. Depending on how you slice, you're either going to have pieces that look like this, this, and this. Or if you slice it the other way, they're going to look like that, that, and that. Either way, you're going to have 3 chunks. Nobody wants that. Bad strategy. Okay, so let's consider another option. We're going to use polar coordinates. By the way, good general rule of thumb, polar coordinates works out great when circles are involved. Not always, but very often, right? Especially if the circle is centered at the origin, or if the circle hits the origin, as both of these do. Okay. All right, so so we just gotta play the well. Don't forget your stretching factor. Again, notice already got it in there. I wrote that down all at once, even though you can't tell from what we have here. But anyway, so there it is. Don't forget it. And we can convert the integrand. Again, that's just a matter of polar coordinates conversions. No big deal there. And now it's playing bounds games. And let's think about the lowest value of theta. The lowest value of theta, well, here's my theta slices. My theta slices look kind of like this, etc. The lowest one is going to happen at that point. I need to understand then what the value of theta is for that point. And if you want to, yes, you can write down the equations of these two circles, set them equal, solve, do a little trig. It's not even that hard. But there is a clever thing to be on the lookout for. Part of the reason I'm doing this example, you just notice, if you're attentive, that this distance and that distance are both radii of a known unit circle, and bad color choice. This distance is a known radius of another known unit circle, right? And so, convenient observation, we're looking at a equilateral triangle there, and because that's an equilateral triangle, it's really easy to see that that angle is negative pi over 3 for that point. Everybody on board? Yeah, so you look for the little bits of convenience. Likewise up here, similar argument, no pun intended. You can make with that triangle, and so upper bound pi over 3. Okay. All right. Okay. What about the inside bounds? We're going to fix a value of theta. The lower bound is going to come from that first point. That point's on that curve, which has that equation. We're looking for r bound, so I'm going to solve for r in that equation, which gives me 1. Right? Keep in mind, we're not focusing here on the answer. We're focusing on the process. Right? So focusing in on the process. Upper bound is defined by that point, which is on that curve, which I do have to do a little bit of work to find the equation of that curve. Right? You can infer the equation for that curve from here. It's what you get when you have equality there. And then you can do the usual chapter 1 style conversion formula or conversion process. I claim it works out to be that. We solve for r in that equation. Again, already solved for, lucky break, and we get that. Everybody good? Okay, this example is of historical interest. It's a cool calculation that first got done several hundred years ago, which is just remarkable, I think, and it is super clever. So anyway, it involves how to compute this integral, and the temptation is to say, well, isn't that just like an improper integral? Can't I do this with Calc 1? And tragically, no. Again, there's that nasty integrand, and that antiderivative is not something you can write down in closed form. So the fundamental theorem does not help directly on this question. Another natural question comes up then, well, how about I just don't worry about it? Right? Do I have to know the answer for every single integral? Right? Well, in this case, actually, this is a really important integral to understand. This function here, this nasty integrand, very closely connected to the idea of normal distributions, which are unavoidably, intrinsically, naturally critical to statistics. And not because we just like the shape of it, but because it really is mathematically, fundamentally natural in very significant ways that I wish I had time to talk about. So this is a really important integral. This comes up in some sense every calculation you do with normal distributions and statistics. You need to know the value of this integral. And we can't use a fundamental theorem, which is our main tool. So this is important and hard problem. So here's the clever move. The clever move is to recognize that if this value I'm looking for is called j, then each one of these factors here is just kind of two copies of j, and thus is j squared. Pay no mind to the fact that one of them is written in terms of a different dummy variable. They're just dummy variables. Right? The alphabet doesn't affect the value of integrals. Right? And then I make a couple innocent observations. For one, this thing on the left is just some value. It's some number, and I can just stick it right inside of the dy integral. No problem. It's just a number. I don't know what the number is, but it's just a number. It's not a function of y. And then now I can look at this iterated integral. I recall that for the purposes of the inside integral, the outside variable is constant, which means for the purposes of that dx integral, y is constant, which means e to the negative y squared is constant. And therefore I can pop it right inside of the dx integral. Which seems like I'm doing some fancy copy-pasty sorty kind of stuff. It doesn't seem too good to be true, but this is all perfectly fine. Okay? The result then is that my integrand is this. You can look at the bounds here. See, I'm now sweeping over the entirety of the entire xy plane, all of R2, which means that the square of the number I'm looking for is this double integral. Now let's take a quick pause and address the progress that we've made here, which does not seem very evident. I've taken a single variable integral that I don't know how to solve, and I've turned it into a double integral that I don't know how to solve. Kind of seems counterproductive. There's a weird strategy trick underlying this, and that is not every time that you make a problem harder is it actually harder. When you make a problem harder, sometimes you put it into a context where there are different tools to work with, and sometimes those different tools that apply now only to the harder version are what make it all work. And that's exactly what's going to happen here. And this is not the only place in math that this happens. But it's a cool trick to be on the lookout for. This being a double integral, we now have the ability to do it in polar coordinates. There is no version of that in single variable. Right? So getting me into this harder two-dimensional world allows me to just say I'm going to do this in polar coordinates. Here's how you write down the entirety of the xy plane in polar coordinates. we find ourselves then looking at this integrand, and there's an easy substitution. You just let that be u. You see du staring right at you. Boom. It's all over but the details. And so what we find here, and this is, keep in mind we were computing the square of what we're interested in. We just computed that j squared is pi, and therefore j is the square root of pi. So super clever, very, very clever computation. And I just think it's cool. Okay, so that's polar coordinates. Now we're going to move on and talk about cylindrical coordinates, cylindrical coordinate integrals. Same deal pretty much. When you're doing an integral in cylindrical coordinates, you're just using cylindrical coordinates as a change of variables function, which means you're going to have a pullback domain of which you will be taking various slices. Those slices will all represent constant values of theta. And constant values of theta are pretty easy to understand. A little hard to draw sometimes, but pretty easy to understand in the XY world. They're just half planes hinged on the z-axis, as we've previously discussed. So again, when I'm doing an integral in cylindrical coordinates, yes, I'm doing a change of variables. Yes, there's a pullback. Yes, I'm slicing up the pullback, and technically that's kind of all happening here. But you can see everything you need in the picture you already have. So why not just do business accordingly in XYZ world? So that's the big idea. There are some similar tips and tricks. Of the 6 different orderings that you can use, these are the 2 that are overwhelmingly as good as anything else. There are some cases where the other orderings can be just as good, but it's very rare to find a situation where there's any advantage to using any of the other 4 orderings. So my advice, always stick with these 2. As a memory tool, I'll point out that this always puts dr d theta together and in the usual order. And so the question is just, do you put dz on the outside or do you put dz on the inside? That's the easy way to remember it. Just leave dr d theta together and in that order. This follows. All right, and again, this is just a hack to avoid inadvertently forgetting and costing yourself points because you forgot something critical and fundamental. Please always write down this entire thing all at once, just so you don't forget the R. It's so easy to do. It's so easy to accidentally forget to put that in there. It's so easy to delude yourself into thinking, I don't need to write down the R now. I'm sure I'll remember to write it down later. And again, very often, I have tons of evidence. Very often students just don't remember. Right? So please don't let that be you. Okay, here's an example. Let's look at this domain right here. It's what I've got in this picture like so. And how would I do this? I'll recognize first, if we use rectangular coordinates, square roots everywhere. Nightmare. Probably. Right? Highly undesirable. Okay, but pretty easy if I do cylindrical coordinates. And just to get the ball rolling, I'm going to use this order right here first. Notice, reminder, dr d theta together and in the usual order. dz on the inside, whatever. We'll do the other later. Let's think about theta. Well, here's a theta half plane. The resulting theta slice, I appeal to your geometric intuition, is like this. That's a theta slice. Another geometric appeal. These kind of go all the way around. You might say they go all the way around because my solid encloses a portion of the z-axis. That make sense? Okay, so 0 to 2 pi. Okay, so as usual, we're going to now fix a value of that variable. We're going to fix theta. We're then going to go on to slicing in the next direction, which is r. What do r slices look like? Okay, wait a second. We got to keep in mind a slice means a constant value of that variable. So what do I get if I have a constant value of r? Well, a constant value of r would be a cylinder, which is weird. A cylindrical slice. Imagine you have like an apple corer, right? You're cutting sort of straight down, like so. Well, again, we're not interested in the slice of the whole domain. We're interested in the dr slice of the theta slice, and that slice of a slice looks like that. Geometric appeal. So, okay, well, where do these start and where do they end? Let's see here. Let me fix my color consistency. There we go. So there's what our slices look like. It starts there, which is obviously, oh, I missed, which is obviously where r equals 0. And it's going to end this this slicing process. Let's see if I can make the light blue show up. It ends kind of at that point, which is, by the way, at a point whose distance from the origin is literally a radius of this sphere. And so that means that you can just see from the picture r has to be the radius, which is a. And so that tells me that the upper bound for r is a. Now let's pause real quick on this. Is everybody seeing the geometry? I'll remind you, in order to be able to see the geometry, you need to have a good picture of the geometry. In order to have a good picture of the geometry, you need to be reasonably decent at drawing good pictures. Please either already be good at that or put some effort into becoming good at that. It's unavoidably valuable in multiple ways that I've already talked about at length. So make sure you're good at that. Okay, now let's go on to this slice of a slice for that value of theta, for that value of r. Let's think about the z bounds. Well, I mean, z starts at that point, which is clearly in the xy plane, where, of course, z is 0, and so my lower bound is z equals 0. We end at this point up here, and now I'm going to have to do some work. That point, let me get rid of that. That point right there, well, it's clearly on that sphere. You're going to have to do a little bit of work to from the statement of the question, infer what is the equation of that sphere. Chapter 1 stuff, right? So flashbacks. This is the cylindrical equation of that sphere. Again, pay diligent attention to the process. A lot of students will mess this up and say, I don't know, they get an idea in their head that, I guess this, I missed. I guess this must be the upper bound or something, but that's not the process. The process is, you have to remember, we're looking for a value of z. We're looking for a z bound, so that's a value of z. So you have to solve for z. That is what is our upper bound. Is that cool? Cool. All right. Okay, so that's That's an example in cylindrical coordinates. Now I'm going to do the same example, this time though putting dr d theta on the inside, putting dz on the outside. This is just our other of our two plausible choices as to which way to slice. That's going to change the geometry pretty significantly. Let's look at our z bounds. Well, z slices all kind of look like this. The first one is down here where I'm going to say it's pretty clear that z is equal to 0. The last of those slices is up there at sort of the North Pole where z is a. Yeah? Okay. So now we fix a value of z as usual. There's our z slice. We now move on to, okay, what's the range of values of theta? Well, theta slices look like that, and again, geometric appeal, they clearly go all the way around. So theta goes from 0 to 2 pi. Everybody happy? All right. And now, slice of a slice and all that, with theta and z both picked there, is our theta slice of our z slice. And so now, again, following the usual process, where does r begin? Well, r begins at that point, which is clearly on the z-axis, where that's the equation, which I can easily solve for r. Again, you got to solve for the variable you need. Again, sometimes you get lucky and it's already solved for, right? But we do want to recognize that solving for r is what gives me 0. The last point, the upper bound, is going to come from that point. Okay, well, we got to think this through. What can I say about that point? That point is, oh yeah, it's on the same sphere, which has the same equation. And here's where another common mistake will come up. A lot of students will look at this and be like, oh, same point, same equation, so I can just copy the bound from the previous example. And no, you cannot. You can't copy from the previous example because this was a value of z. I am not looking for a value of z. I am looking for a value of, oh gosh, I can't get the thing to cooperate. I'm looking for a value of r, not z. So this time, because I'm looking for r, I've got to solve for r. And that's what gives me my upper r bound. So it's different. Is everybody good? So again, the process is critical. If you don't follow the process, you're going to write something down that, looks more like a symbolic manipulation recognition and less like an actual mathematical argument. And again, that's not what we do here. Yeah. Okay. All right. How are we doing on this example? Any questions on this example now? Okay. All righty. Spherical coordinates. Same story. Third verse. It's the same. It's just now it's different variables. It's still a change of variables function. We're still going to be pulling back. We're still going to be, for example, doing theta slices or phi slices or what have you. And I can still, just like in the previous cases, I can still see what they look like in my existing XYZ picture. So we just have to think through what those slices look like, and I appeal to your sense of geometry. Theta slices still look like that. It's the same theta. Phi slices. Now this is weird. Phi slices are going to be kind of cones, because keep in mind phi represents the angle off of the z-axis. So a constant value of phi would give you points on cones like this, because every point on such a cone has a constant value of phi. Does that make sense geometrically, everybody? Okay. And then a little scary, but this is what row slices would look like. Row slices are little spheres. And it's hard to visualize what kind of a knife would make a cut like that, right? So the word slice kind of becomes a little sketchy here there. But anyway, this is how we have to visualize row slices. And this is undesirable. But here's the good news. You don't really need to draw those kinds of pictures because, as it turns out, rare exceptions granted. For our purposes, practically always, this is the order you want to do the differentials. D rho d phi d theta. Which means you're going to be doing theta slices. You will then be doing phi slices, but not of the whole thing. You'll just be doing phi slices of only the theta slices. And then, etc. So let's look through and see what this looks like then. Here's a theta slice. What does it look like if I were to do a phi slice of this theta slice? And, well, it would just be that. It would be a little ray coming out of the origin. So even though these slices are pretty weird looking, the only slicing order we're ever going to use is going to make them show up really only in that way right there. So not that bad. Does everybody see what I'm doing there? Okay. And then likewise R slices. Well, I mean, row is going to start at 0, and then we're just looking at basically distance away from the origin. Okay, and then I'm also going to point out, after this good news, that this is always the order we do. We likewise always write down this whole thing all at once. It is so easy to forget the stretching factor, by which I mean not necessarily you'd forget the formula for it, although that's also possible, but that you'd just, space out for a minute and forget to insert it in the first place, right? So please write down this whole thing all at the same time. You want to try to memorize this whole thing. Think of this as a single object, which, by the way, is dx, dy, dz. So it's a natural object. But write this whole thing down all at once so you don't forget your stretching factor, if only. All right, let's keep that in mind, and here we go. Got a domain, a ball, off-centered, centered on the z-axis. Okay, all right. So, but by the way, we could try to do this in cylindrical coordinates. That would be a reasonable option. It's not going to work as well as what we're about to do here, but anyway, it's reasonable. So first thing, we do theta slices first. As previously discussed, this is what theta slices look like. Right? They're half planes hinged on the z-axis, like so, giving us then slices that look like this. And geometric appeal. I argue that those go all the way around. Is everybody seeing the geometry, by the way, that I'm so very important to use your geometric intuition to visualize what these slices look like and to see from the picture how far around, in this case all the way around, that they go. Okay. All right, so got our theta bounds. All right, proceeding along. Now, we could talk about phi slices of this theta slice. And we could try to draw pictures like this. And that's fine. And that's what phi slices look like of our theta slice in this picture. And no problem. But I have to point out, I find something a little bit confusing about this picture. And in particular, let's think about this sort of the largest value of phi right there. It really looks like it's pointing downward. But then if you take your time and think about this three-dimensionally and visualize, notice, no, actually that's parallel to the XY plane. That's actually perfectly horizontal. But it looks like, if I'm just at a casual glance, it looks like it's pointing down. And it is possible to outsmart yourself by just not having quite good enough of a picture and just not quite seeing things right because of basically perspective, right? This is the fault of imperfect ability of a mediocre attempt at perspective drawing to represent a three-dimensional thing. Okay, so my workaround on this, and again, you do not have to do this, but I find this helpful, and I encourage you to do this, is to redraw your theta slice. There's how I take a theta slice. This is the resulting shape. I'm going to redraw exactly that, looking straight on at it, instead of looking at some, askew angle. I'm going to look right at it. And by the way, you can think of this sort of, if you will, as sort of being an R-axis. Not that you have to, but that's just to help you kind of get your bearings. And now let's think about, what do our phi slices look like? Well, these phi slices that were a little hard to visualize there, those phi slices here are much easier to visualize. And I can just immediately, intuitively see that my last phi slice is, you can see it right there. It's horizontal. That's pi over 2. No confusion. Everybody see what I'm doing? Okay, again, you don't have to. Again, I encourage it. Okay, if I can get that thing to delete, there we go. Okay, now we fix both theta and phi. We are now focusing our attention on that phi slice of our theta slice. We got to think about the range of values of now rho. And rho starts at that point where I think it's pretty clear that that's where rho is equal to 0. It's the origin. So, yeah. Is that cool? Now let's think about the upper bound. Here's where you got to do some work. The upper bound for rho comes from that point, which is on that curve, which is actually, let's remind ourselves, I got to see if I can, there we go. That curve is actually this curve I just kind of redrew, but we want to remind ourselves where that all came from on our original picture, which is on the sphere, of which I can write an equation given what I had there. I can write down the rectangular equation, which I can then convert into spherical coordinates. And make sure you can do this. Right? And again, that's chapter 1 flashback. Converting a rectangular equation that would be easy to write down into the spherical equation that we need for what we're doing. And with that noted, then keeping in mind, we're looking at this point, which is on that curve, which comes from a surface with that equation. Wait a minute, what am I doing here again? Why am I writing this down in the first place? I find it very easy to lose track. I'm trying to find a value of rho. So I solve for rho in that equation. And that gives me my upper bound. Cool? I've made this point several times, but I'm going to do it again. Make sure you can draw a good picture. Don't underestimate the value in making it big. Use some space. Paper's not that expensive, right? It's really, really useful to have a nice big picture. Take care to make it a clear picture, right? Just the ability, there's kind of a magic psychological phenomenon that happens when you take a picture and follow certain rules that make it just pop, and all of a sudden, I see three-dimensionally now. Right? That's some weird psychology going on in your head that's not automatic. It's only if your picture is sufficiently carefully, clearly done that you get that super valuable benefit. So please take it seriously. And then, by the way, for whatever it's worth, don't feel that you have to just instantly write down a perfect picture. I certainly don't. I usually sort of write something. I try to draw my first attempt at a picture just to help myself get a geometric intuition for it, and then realize what I did wrong as I was attempting to get my geometric intuition, and I then redraw it. Sometimes several times. Some of you all have been in my office hours recently and have seen me do this using 3, 4, or 5 sort of repetitions of the process. So there's no shame in doing several attempts. So I would encourage on exams, for example, don't forget you're going to have scratch paper, right? Plenty of scratch paper at the back. Use that, for example, to draw multiple pictures to help you figure out how best to draw what you're working with. Okay. Lastly, there are things to know. Drawing is not purely a matter of talent. It's just not. There's techniques, there's tricks. Learn the tricks. Now, my YouTube video is my best whack at explaining all the tricks that I know. So I encourage you to take a look at that for that reason. But feel free to look elsewhere for 3D mathematical drawing tips and tricks. And also, this is something that requires practice. And so as you're, for example, doing homework exercises, think of the drawings that you're making not just as something that will help you get the answer to that homework question. Think of those drawings that you're making as practice for drawings that you'll need to make on the exams, which will help you get, good progress, good ideas on the exams. So, and you might even give yourself more practice than that. That'd be perfectly reasonable. Okay, speech over. Another example. Let's see how we do on time. Okay. Here's another off-centered ball. This time centered over here on the y-axis. Something kind of like that. And again, let's slice this up. Slice this up in spherical coordinates. Oh, by the way, real quick, there we go. Notice stretching factor already included. Don't forget. Write this down all at once so you can't forget. Really valuable, really important. Okay, so we take our usual theta slices first. This is what a theta slice looks like. And now, again, I have to make just a geometric appeal here. The origin, sitting over here like that, is not surrounded. The origin is just kind of on the boundary of this ball. Right? You can imagine, for example, there is a tangent plane. There's a tangent plane to the ball right there at the origin. And so our theta slices are going to kind of start there, where theta is 0. They're then going to kind of go around like that, and they're going to end when theta is pi, not 2 pi. It does not go all the way around. When you get to pi, you're done. That makes sense? Purely geometric appeal. You've got to see it from the picture. Okay. Right. Okay. Right. So then, as usual, we're going to focus now on a single theta slice. I appeal to your sense of geometry. Any sort of flat slice of a sphere is going to make a disk. Of a ball makes a disk. Again, I like to redraw these just for, I find it a little easier to visualize. It's not that you have to, right? But there's that same theta slice. And with that in mind, and keeping in mind that the z-axis is like so, now let's think about our phi slices. And our phi slices, they start at 0, and then they kind of keep going. But then they keep going, and then they keep going, and then your last one is going to be straight down. So again, 0 to pi for our phi bounds. Cool. All right. Okay, and then again for our phi slice of our theta slice, looking on that thing right there. We start there, which of course is actually there. So we're starting at the origin, where of course rho is 0. And then let's see, we're going to end there, which is on this curve, but really more to the point, it's on that curve, which is really on this sphere. And again, there's some work to be done to take this information, to write down the equation originally in rectangular coordinates, and then to convert into spherical coordinates, and you get this. Now, make sure you can do that. Right? That's not automatic. There's a significant Chapter 1 effort involved in that. So I think it'd be a great practice problem, right, to make sure that you can do that and that you do get this right equation here. In which, keep in mind, we're looking for a value of rho, and so we solve for rho, which conveniently was already solved for, and then our upper bound is that. Everybody buying it? Okay. Last example. This is mostly a matter of the artistic trick that is really useful in this example. So I want to point out this is really hard to draw, which is part of the reason that I feel like we're going to need the artistic trick I'm going to show you. But keep in mind, what we're looking for is points, as indicated here, that are outside of the unit sphere but that are also inside of this other sphere. Right? And now you just got to think about the geometry of this. And okay, we want points that are inside of that. We want points in that blue ball, but only the ones that are not in the green ball. And I think it is pretty satisfying that the points that are outside of the green but inside of the blue are these kind of right like this. Everybody see that? Okay, now here's where things get weirder. How do I draw that thing? And if I draw like this, I claim there's something really, really wrong with this picture. This makes it look like I've cut out a cylindrical hole in the bottom of the sort of the larger ball up there, like there's nothing in there. But that's not true. I have not cut a cylindrical hole in this. What I have, imagine you have an orange or something, right? And then imagine you take an ice cream scoop and you're going to scoop out not a cylindrical hole, but a spherical hole from the bottom of it. And I claim, in fact, it would actually have kind of a lip down here, like that. And the problem with drawing it is if I draw that whole thing, well, then look what it looks like. It ends up looking like it doesn't have a spherical hole cut in the bottom of it. It looks like it's got a flat bottom. This is hard to draw, right? It's not like even that the artistic talent is the issue. It's just we don't really have tools to allow us to draw what this solid actually is in a perfectly obviously natural way. So this thing, it's hard to draw. Now apparently I've got to actually figure out how to not only draw it, but to draw cross sections of it, right? So this weird thing, whatever you're going to do there, you've got to imagine how would you take theta slices of that thing, and oh my gosh, it's easy to get confused. So here's the big trick, the really nice trick. We are looking at an intersection of two things. We want to take a cross section of that intersection. The neat trick is I can look at the individual cross sections and just intersect those. Oh, I wanted to switch colors. Just intersect the individual cross sections. Let me show you what I mean by this. Let's start with the theta slice of this. Colors. Theta slice of this ball here. How would I take a theta slice of that ball? And I say, oh, that's super easy. It's a full, solid ball. I'm cutting it with a half plane, nothing to it. And what I get is a half disc. No problem. Everybody see that part? That's easy. Okay, now wait a second. Let's look at the other thing that I need to take a cross section of. This blue ball down here. What happens when I take a theta slice of that blue solid ball? Well, that just gives me this blue disc, half disc, down here. And now that I have these cross sections drawn, right, I just need to look at sort of the intersection of the cross sections. What's inside of the orange but not inside of the blue? All right, nothing to it. It's just that right there. So notice I have found the cross section that I'm interested in without ever having to draw the original solid. Without ever having to draw the original solid well. Anybody see the trick? That's the main point of this example. I do want to encourage you to think through the rest of these details. Make sure you can see these bounds. As always, of course, you'll notice that I got this all written down together. I put my stretching factor in there as I was writing down my differentials. I do not trust myself to remember it otherwise, right? And I encourage you to do the same. So make sure you can make sure you're good with those bounds. It's just like all the other examples we've done. Makes good practice. Okay. So we now have 15 minutes, as I had hoped, to talk about symmetry theorems. So now this is like 5 pages of notes on symmetry theorems. It's way more detailed than it needs to be. When I have loads and loads of time, I like to talk through those details. We do not have loads and loads of time. I don't know if y'all have been paying attention to the class schedule. We're a little behind. So I'm in tough choices mode, and so I'm going to give the quick, intuitively satisfying, good enough, more than most 219 instructors give version of these symmetry theorems. This is a personal sort of like pet peeve. That's the wrong word. Soapbox, I think, is the right word. This is one of my soapbox topics. I think the symmetry theorems are wildly underappreciated in multivariable calculus classes. They're super useful. Just to give you a perspective on how useful I think these are. Y'all recall I had a second major in physics. I talk about that a lot because it's relevant to how I approach this material. In that second major in physics, I took 9 physics courses, which made me do just an incalculable number of integrals. Right? Lots and lots and lots of integrals. Y'all are largely engineers. Y'all are going to be doing lots and lots of integrals as well. My back of the envelope best estimate based on my memories is that about 20% of the integrals that I saw, I could instantly write down that integral is 0 by way of a symmetry argument. 20% of the integrals that I saw. That makes this a super, super important computational tool, right? And I think that's a conservative estimate, frankly. I think they come up so often. So anyway, I think this is way underrepresented in textbooks, and that's why we're going to discuss it. But I'm not going to go through the full thing. So I'm going to remind y'all in single variable calculus of this theorem. If you have an odd function, the colors. If you have an odd function, and if it is on a symmetric, you're integrating on a symmetric domain, then the integral is 0. How about that? Right? Sweet theorem. I hope you all have seen this. It's pretty standard single variable calculus theorem. Sometimes, not rarely, you'll happen to have a function with odd symmetry and a symmetric domain. And the argument as to why that works is you just look at the terms in the Riemann sum, and this term here, that term there, and this term there, because of the oddness of the function, because this curve, is odd, the value of the function there is the negative of the value of the function there, and this minus. The colors, come on, man. Red. Okay, so because of this minus sign, those terms cancel in the summation. Right, the green is the exact opposite of the blue, and then everything cancels. So that's the big idea. All of the symmetry theorems that we're going to see here turn on exactly that idea. Now, you can think of that from a change of variables point of view. Specifically, if you just make this substitution and you can go through the argument, it works just fine. The integral is 0. This is one of these things we're not going to have time for here. But what I'm going to do is just point out there's a two-dimensional version of this morally exact same theorem. It's based on the idea of a reflection, and when you have a line, a reflection is exactly what you think it is. It's a function that takes any point and just straight up literally reflects it over that line. It's exactly what you think geometrically, just like when you look in the mirror. Is that believable? Okay. Well, there is a notion of oddness. Odd means that you get a minus sign when you reflect the input. Shameless ripoff of the equivalent idea for single variable. There is an idea of a symmetric domain. A domain being symmetric, you're going to see pictures that we're about to talk about. Just Rorschach test, right? You draw the line, goes right down the middle, and it looks the same as you reflect. Right? So, not surprising, we have a very analogous theorem. And specifically, if you have an odd integrand and if you have a symmetric domain, then your integral is 0. How about that? Super convenient, super powerful theorem. You could be looking at a double integral. You could have an ugly integrand. You could have a weird-shaped domain. And as long as that weird-shaped domain is symmetric, as long as that ugly integrand is odd, we'll talk later in a moment about how to test that. You wave your magic wand, that integral is 0. It's just totally awesome. Now, do be careful of the couple of delicate aspects of this. For this theorem to work, you do need, critically, both of the conditions. So often, oh my gosh, so often I see students, they see a domain that they identify as being symmetric, and then they just declare the integral's 0 by symmetry. It just doesn't work at all. Got to look at that integrand. The integrand has to be odd for that argument to hold any water at all. So, careful. Make sure that you think carefully about both of the conditions. The other common mistake that I see, tragically all the time, you've got to be using the same line for both of these symmetries. It is not good enough, not even close to good enough, for the function to have symmetry over one line and the domain to have symmetry over a different line. It's just, there's no good. Doesn't work at all. So again, you can take a change of variables point of view on this. We don't have time. Take a look if you're interested in. You can take a Riemann sum point of view on it, very similar to what we argued previously. This term in the summation and this term in the summation, because of the oddness, are negatives of each other, and because they are negatives of each other, they cancel in the summation. Exactly kind of what you would sort of expect. Okay, so let's see this in action. Here we have a nasty integral that you really don't want to have to deal with. You do not want to have to work out this integral over that domain, right? If you had to do this the old-fashioned way, wow, rough one. All right. Well, let's draw a quick picture. Now, y'all know how to curve plot. I'm not going to rewind to Calc 1 and remind you how to draw curves, but hopefully y'all remember how to draw these curves, and I'll just give you the punchline. Those curves. Let's see here. So this one here looks something like that, and of course this one is something like that, and so this domain that's bounded by those is what's in between, like so, and I think it's pretty intuitive geometrically that that's symmetric over the y-axis. Everybody see that? It's a weird shape, and it's undesirable in a lot of ways. It's got a quartic in it, for crying out loud. Symmetric, pretty clearly. And you can look at it, if you want an algebraic argument, boom, go ahead. There it is. So next, let's think about, okay, if we're going to do a reflection over the y-axis, get the y-axis back there. There's the y-axis. A reflection over the y-axis is like this, and notice the reflection over the y-axis effectively just pops a minus sign onto your x-coordinate. Right there. The y-coordinate stays the same. The x-coordinate gets a minus sign. By the way, watch out for this little, it's real easy to mess this up. It's real easy to say, I'm reflecting over the y-axis, so I get a minus sign on the y-coordinate, but you don't. It's the x-coordinate. It's real easy to mess that up. So please be careful. And then notice if you pop that minus sign into where all the x's are, and if you compute and rewrite, and then sure enough, this function's odd. So this nasty nightmare of an integral, we make a couple of clever observations, and that integral is 0 by symmetry, and we drop the pen and walk away. Right? No nasty effort. A little bit of effort. Nothing bad. Everybody see the power here? Totally awesome. Now, let me, I'm going to have to do some editing on what's written down here. This discussion right here notes my policies on what I require for you to give me a complete symmetry argument in the circumstances where I have time to talk through all the details as much as I wish I had time, which is not this time. So y'all are not actually responsible for all 5 of these. Y'all don't have to do any of these. The policy, it's just, so you have to you have to think it through, right? I'm not saying you're not responsible for truth. I'm saying you're not responsible for documenting, right? So all you have to do is tell me you're making a symmetry argument. Tell me what the line of symmetry is, and you have to be correct. Right? Again, you can't just claim there's a symmetry argument when there is no such symmetry. No, of course not, right? So anyway, just make sure that you tell me what the symmetry argument is, and the rest of it you just think through. You look at the picture, you persuade yourself how this is working, and then go ahead. I do warn you, though, it remains unavoidably that symmetry arguments are dangerous. So please be careful. What I have seen a million times is students look at an integral and they're like, oh, hey, this looks like integral 0 by symmetry over the y-axis. Well, if there is no symmetry argument that works over the y-axis, nothing the student has written down is true. Nothing the student has written down is in the direction of a valid solution. I can't give partial credit. There's nothing that's right. Right? So you can put yourself into this dangerous scenario of you thought you had it, therefore you didn't exert any more effort toward it, and therefore you didn't get any of it right just by making this one little easy to make little mistake. So if you're going to use a symmetry argument, I implore you, please think carefully. Right? Make sure that actually works. Otherwise, you can really hurt yourself really badly on a test. So we're going to scratch off this example that follows here, because this is discussing requirements that y'all are not responsible for writing down. So this was mostly just for that purpose. And let's see here. Yeah, we're out of time, so this is a great place to draw the line. I have a few more examples to show you of symmetry arguments, and then we'll proceed along. Oh, okay, so real quick, before we go, today, believe it or not, is the last day of fair game material for Exam 2, which is on Monday, which is kind of blowing my mind. I feel like we just got finished with Exam 1. So anyway, we did not finish this stuff about symmetry, but we did finish all this coordinate system integral stuff. So what you're going to notice on the calendar, which it'll take me too long to pull it up, but on the calendar, the color coding, remember, on the calendar tells you what is fair game. And so you're going to notice that 5.5's first two parts, namely change of variables and coordinate system integrals, are going to be fair game for the exam. The symmetry stuff will not be fair game for Exam 2. Of course, it'll be fair game for Exam 3. Okay, see y'all later. Have a good one.